All right, let's get right into it. Today, we are going to peel back the skin and look at the microscopic secret behind every single thing you do. I mean, every movement, from a tiny eye blink to a massive deadlift. We're talking about the sliding filament theory. So think about this for a second. How does a simple idea in your brain, like I'm going to pick up that cup of coffee, turn into an actual physical force? It kind of feels like magic, right? But it's not. It's just some of the most elegant biology you can imagine. To figure out this mystery, we've got to zoom in, and I mean way in. We're going deep, deep inside a single muscle fiber to see the tiny machinery that actually makes all of this happen. And here we are. This little repeating structure you see, it's called a sarcomere. This is it. This is the basic, fundamental unit of a muscle. Every ounce of force your body can create starts right here, on this tiny, tiny little stage. Now, on this stage, we have two main characters. You've got the thin actin filaments. Think of these as the ropes or the tracks. And then you have the thick myosin filaments. These are our pullers, and they're covered in hundreds of tiny little heads that are about to do all the work. So, we've got our stage, we've got our characters, now it's time for the show. We're about to watch this incredibly fast, super elegant process that scientists call the sliding filament theory, but I like to think of it more as a dance. And this dance happens in a super fast four-step loop. First, one of those myosin heads reaches up and attaches to the actin rope. This connection is called a crossbridge. Then it pivots, bending with some real force and pulling that actin rope in towards the center. After the pull, it has to detach, letting go of the rope, and finally, it resets, snapping back to where it started, ready to grab that rope again, just a little further down.
You see, it's not just one big yank. The best way to picture it is that the myosin literally walks along the actin filament. Each step is tiny, but it's this constant, relentless walking action that slides the two filaments past each other, making the whole sarcomere shorter.
So how many of these little pullers are we talking about? Well, this is where it just gets insane. In just one of those thick myosin filaments, there are more than 600 of these little heads all ready to work together. And they are ridiculously fast. Every single one of those 600 heads can go through that entire four-step cycle, attach, pivot, detach, reset, about 5 times every single second. You do the math, that's thousands of little power strokes happening every second in just one filament. The level of coordination is just, wow. Okay, but all of that high-speed action, all that pulling and resetting, has to burn an incredible amount of fuel, right? Of course, this whole process would grind to a halt without a constant power source. So what's actually fueling this incredible molecular machine? Well, the first thing you absolutely need is calcium. When your brain tells a muscle to move, calcium floods the area. You can think of it like a key. It unlocks the specific spots on the actin rope where the myosin heads need to grab. Without calcium, those spots stay covered up, and the whole process can't even start. So if calcium is the key, then ATP is the actual gasoline. This molecule, adenosine triphosphate, provides the power for that myosin head to pivot and pull. But, and this is super important, it also takes another molecule of ATP for the head to let go and detach. So it's the direct energy for both grabbing and letting go, for every single step of that walk. The body obviously needs a non-stop supply of both, and our bodies are pretty clever about it. Our muscle cells keep their own little emergency stashes of calcium ready to be released. Those are kept topped up by calcium from our blood or even our bones if things get serious. And the ATP? Our muscles are constantly making more of it on the fly, keeping that engine humming. Okay, so we've been way down in this amazing microscopic world. Let's zoom back out now and see how all these tiny little pulls create the actual strength we use every single day. And really, this is the main takeaway. That huge, powerful force you feel when you lift something heavy, it's nothing more than the grand total of trillions and trillions of tiny myosin heads all walking along their actin ropes, all at the same time, all in perfect sync. That's what shortens the muscle. It is just an unbelievable piece of biological engineering. So we've seen this beautiful system. We know it needs a constant supply of fuel, calcium as the key to start it, and ATP as the energy for the pull, and crucially for the release. Which brings us to a final question to chew on. What do you think happens when that fuel starts to run out? What is muscle fatigue at this tiny molecular level?
And think about this. If you need ATP to let go, what happens if you run out of it completely? That's something to think about.